All right, the recorder is on. It is noon, so we're gonna get started. Okay. Um, does anyone want me to go over the exam, or do you guys just kind of want to move on to the next topic? Huh? The grading is gonna be a while, but I can at least tell you guys which one is which one. I mean, so you can kind of get an idea of how you did. Yep. Yeah, sure. We can start with question number six. All right. So question number six is a Star Trek question without copyright infringement. Okay, so I'm gonna read the question and let's zoom in a little bit just so that people in the back can read the entire thing too. All right, so Captain Jerk decides to use the space folding or Cantor's pairing. Okay, are you guys ready? Thank you. AKA also known as Cantor's pairing function, which is also known as function G in the Aleph No module. um, to slightly encrypt three-dimensional natural number-based coordinates using a bijective function h, which is new to you. So h is going to take n times n, which is basically the Cartesian product of n three times. It maps to n. There are 12 ways to do this in no particular order. So this is the list. These are the 12 ways to utilize a nested call to G in order to fold a three-dimensional space coordinate into a single natural number. All right, so do we have any questions up to this point? The setup? Well, you apply. Okay, so we'll take the first one as an example. And by the way, everybody has a different list, which is completely randomized. So if yours doesn't look like this, it's completely normal. All right, so we'll take this one into consideration. So the h function is defined as the g function applied to two natural numbers. The first natural number is simply z coming from here. The second natural number is the result of applying g to y and x in that particular order. Is that okay? So it's a nested call of g, in order to fold three numbers, three natural number, into a single natural number. And there are 12 ways to do it. So are we good so far up to this point? All right. So an operative of the Klingon intelligence unit found that in a particular instance, H of 648 is 2476. And once again, this number also varies because I make multiple variations of this test. Okay, so the question is asking, explain step by step how you resolve the actual definition of function h. Quote equations slash definitions and use logic to explain your reasoning to fellow Klingon citizens. And you do not have to write your answer in Klingon. All right, so how do we do this? So the first thing we notice is all three numbers are unique. I do not repeat a natural number twice in the example that I give you. So pretty much the only thing you can do is to apply G inverse. Okay, so we'll go ahead and apply G inverse to this specific number, which is 2476. And I cannot remember, the G inverse function myself. So that means I'm going to have to, look it up. So we'll go look for Aleph, no, the module. Okay, open it up. Okay, and then we'll look for the inverse function. So I'm not sure whether this will work. Nope, it does not. How about that? Nope, does not work either. So I cannot really look into the LaTeX format of the function. That's okay. I can just go ahead and look for it. Okay, there we go. All right, so the first thing we need to do is to figure out what is W of n. And in this case, W of n is the floor of the square root of 8 times n plus 1 the whole thing minus 1, the whole thing divided by 2. Okay, so we're going to do that. Okay, since I do not have a calculator, I have to cheat a little bit and use a spreadsheet for this purpose. So I'm going to make a new spreadsheet for today using today's date. So this way, if you ever need to look up how we did this, you can actually just look it up. Today is the 2nd of March. So spring break is approaching. I don't like spring break because it uh, it interrupts the momentum of classes. Essentially, after spring break, nobody remembers what we have been talking about the week before. Yep. So to me, it is a problem. Hmm? Sorry? I would much prefer not to have spring break and then have the actual summer break to start in a week earlier. But that's just me. All right. So we're gonna say, what is n? So n in this case was what? Let me see. Go back to the first 2476. Okay, so 2476. Okay, there we go. And then the next thing we need to do is to calculate, W of n. So I would see if how much I can remember. I know it is the floor of something, and this something involves, some numerator divided by 2, and in the numerator, there's a square root of something, I think plus 1? Is it a plus or minus? Okay, we'll double check. I believe it is plus 1, but we will double check. Okay, so it is a minus 1. Okay, so I was incorrect. Okay, that's fine. It's okay. So it's a minus 1. And then inside there's a plus. Okay, so inside here we have 8 times whatever n is, which is this number, the whole thing plus 1. Okay, I believe that's the whole thing. So in this case, it is 69. So w is x plus y. So we know x plus y is 69. So at this point, you can use one of two approaches. You can either just go with this approach here and just plug in 69 into Wn and then just use this equation. That's one thing you can do. So I'm going to follow this step first just to make sure that this works. Okay, but then I will also teach you how to do it in the other way. All right, so the first one is a plus 3 and then the whole thing minus n. Okay, so okay, I'm gonna have to cheat a little bit here because I can't remember something that complex. My short-term memory is very short-term. And this is why taking notes is kind of important to me. So there we go. Always visible. Okay, there we go. Stash it here. Go back to the spreadsheet. Okay, that's so now x of n is going to be um, basically this number. Oops. Okay, that's my bad. Okay, Control Z. Good thing we have undo. So it's equal, okay, open paren, this number times this number plus 3, and then the whole thing divided by 2. And don't forget minus n, which is this number here. Are we good so far? Does everybody, relate the spreadsheet formula to um, G inverse that is quoted at the upper right-hand corner? Okay. So press the enter key. So x is actually 8. So now we try to figure out y, and y is, okay, equals to this number minus, and then we have something divided by 2, and then inside that something is going to be the 69 times the 69 plus 1. Yep. What? Hmm? No, I did it correctly. This n is the b1, and then b2 is the wn. Oh, let me see it. Okay, so it's not working right now. Um, so let's see. What did I mess up? Well, No, it works. Okay, I take it back. It works. The reason why I know it works is because when you add x and y, you should get w back. 68, 61 plus 8 is indeed 69, so it does work. Okay, so now the next question is, how is this helping me to find the answer? Okay, so to answer that part, I'm going to use the whiteboard because it's just a whole lot easier to use the whiteboard for this part. So what we know is G inversed applied to 2476 is a coordinate of 861. Okay. Are we okay with that? Does everybody understand that once we apply the inverse function, it looks like this, right? Okay. So now you go back to the original question. Okay, so you go back to the original question, and then you ask, okay, not this one. The question is right here. So the original question is, oh, that's where the 8 is our z. Okay, so that means the h function is okay. So that means the h function is okay. If h is applied to xyz, we know that this is the g of the z and something. Okay, so I'm gonna pause right here. Does that make sense to you? Okay, because given the original example, which is in the test, we have 6, 4, 8. But once I apply the inverse function to the h of 6, 4, 8, we end up with 8 and 61. So that means, we have 8 and 61 as a two-dimensional coordinate for the g function to work. And therefore, I can map z to be right here. Are we good so far? Okay. So when you look at the list of all the possible ones, now we have focus. We can basically narrow down to either the first one or the fourth one, because both of those start with a Z and then another nested call of G. Let me use a mouse pointer to kind of emphasize what we are talking about. Z is not nested. Z is also not nested as the first thing. Are we good so far? Okay. So now what you have to do is to take this 61 and then apply the inverse function again. Okay. So since I have the spreadsheet already, and since I did specify that you could bring a graphing calculator, which is usually programmable, so that means, if you prepare for this, then you just have to plug this in. Okay, you just say, okay, what if this is 61? Oh, if it is 61, then we have 4 and 6 back. So that means, G inverse of 61 is 4, 6. Okay, 4, 6. So what that means is this 61 here is G of 4, 6. 4 is Y, and then 6 is X. So that means I can now resolve the question mark to become G of Y, X in this case. Yep, yep, exactly. But well, in that case, you won't be able to resolve because you really need to know the 8 is the third in the three-dimensional, tuple, and then 4 is the Y, and then 6 is the first, or X. Yeah, so this order has to be known, and these specific values also have to be known, and this has to be known in order to resolve back to what the original definition is. Yep, yep. Well, I mean, first of all, the final exam is not comprehensive, so this is the only one time when you will have a question about the G function. um, but it doesn't mean that it is not meaningful to use AI to try to work this out. Okay, if not for anything else, you can assess whether the AI can actually understand the question and be able to figure out the answer. I think that is actually pretty interesting. Uh-huh. Yep. But I think it is important to understand how this works, right? To understand, okay, given that we have the definition of G, we have the definition of G inversed, and given that H has to be one of these 12 possibilities, and given that this is known, okay, so some spy actually got this, transmission, and they know H of 68648 is exactly 2476. How do we reverse the whole thing? So this is about the application of the knowledge that we have learned in this class. So um, that's kind of the usual thing that I do in my exams. Okay, it'll be based on the knowledge that we talk about in class, but it is a problem-solving session that is the process of doing the problem solving is usually something that I have not talked about in the class. All right, any questions about this? Do you think this is the kind of thing that you need when you are out there working? It is the concept of being able to work with the knowledge that you have learned already and being able to apply that to do a problem solving session that is important. Now, is it likely that you will ever need to know Cantor's mapping function again? The answer is probably no. It's just like, with yoga, okay? Are those yoga posts ever be useful in any way in real life? Well, maybe when you need to fix your car and you need that flexibility to get to a certain component, maybe it'll be useful. But for the most part, no. Okay, for the most part, it is for just making sure that your joints are healthy, your soft tissues are healthy, and so on. So that's basically what we are doing here. Okay, all the classes are only here to help prepare for the unpredictable nature by the time you graduate in the workplace. In the 80s, the workplace was 100% predictable. Okay, we know exactly what the job is going to look like, what kind of problem we're going to solve, what kind of tools we're going to have, and so on. That is not true anymore. What just happened last week? Why did Anthropic became headline news last week? Yep, yep, exactly. And then OpenAI swooped in and go like, well, if they won't play, we are going to play. And they ended up with a lot of account or subscription cancellation, as they probably expected. But I don't think end user subscription amounts to anything that is actually consequential compared to a Pentagon contract. So so that's the thing, right? Um, but anyway, the reason why I mentioned that is you will need this kind of flexibility of thinking when you graduate. That is what your workplace is going to require of you. Okay, so in this class, okay, so let's just say that, okay, I cannot figure out this question. You still have the other five questions, and those are, I would say, a little bit more predictable and easier, right? So when you're working and you go like, I cannot solve this problem, what is the stake at that point? It's going to be your job. Exactly. Okay. So basically, you have to take a look at, okay, what does it look like from the employer's or my boss's perspective? Okay. If a person is not performing, how many people are lined up, to take that job from this first person? In the 80s, the number is negative. Okay, your boss actually want you to stay because there's no one lining up to take that job. Okay, that is not true anymore. Okay, it's not true anymore. Has anyone heard about 996, which is a work schedule thing in the Bay Area? It is ongoing right now. Yes, 996 refers to 9 a.m. to 9 p.m., 6 days a week. So if you think studying is difficult, working, unless that is exactly what you like to do, then you're going to like a theme park every single day. Okay, that's how I felt when I go to work in industry. It's like every day it's like going to a theme park, and except somebody's paying me instead of me paying the theme park. Okay, so that's 996, and I don't think it's sustainable. Okay, I think by the time you guys graduate, that culture might change a little bit, but right now everything is unpredictable. Okay, so that's the sort of thing that I want you guys to know at least. Okay, now what you do with that knowledge is entirely up to you. Okay, but it is not fiction. Okay, this is actual what is happening in the Bay Area right now. Okay, so getting back to the exam, do we want to take a look at least one of the other questions, one of the other five? Number five, okay. It's all different, right? Each one of you has a different number five and a different number four. So yeah, it takes the least amount of scrolling. So we'll do that. Sure. Okay. All right. So this is the number five of exam 000. Okay. But the key is reading the quantified expressions. Okay. So with part zero, what is that doing? There exists a W in X such that for every two tuple UV in F, W does not equal to U. So now we want to analyze exactly this quantified expression, and then you first have to find kind of feel which category does it belong to. Does it belong to the category of whether F is even a function or not? Or does it belong to the category of assuming f is already a function, whether f is a injection, or assuming that f is already a function, whether f is a surjection? There are the three categories, and that part has not changed since the practice exam. Okay, so let's read it again. This is basically saying there is at least one element in what we think is the domain of f, such that what? Such that for every two tuple in F, W does not equal to U, where U is the first item of the two tuple. In other words, it is asking, are we missing at least one element in the domain so it doesn't map to anything? Is that okay? So as you point out correctly previously, this relates to whether F is a function or not. Okay, and this needs to be false in order for f to be a function. So are we good with that interpretation? Okay, so in this case, is it true or false? Okay, so let's take a look. This is C maps to H, we good. This is J maps to K, we're good. Oh, C, by the way, maps to two things, right? It maps to H, it also maps to K, but it's okay. I just need it. Yeah, exactly. So it meets that requirement. Okay, this is false, so that means the entire thing is false, which means we're good. Okay. What about H? H maps to D. So for every element in X, it maps to something, or I can find at least one thing in UV in F where the first item matches the element in X. Okay, so that means okay, so it passes this test. Okay, the actual value of this quantified expression, which is the exists w in x, that would be um, false. Okay, because for every w in x, we find um, let me let me think about this a little bit. For every w in x, it doesn't match. It matches none of the two tuple of f. Okay, that's basically what it's saying. So for every w in x, it does not match any two tuple in x. So this would be false in this particular case. Okay. All right. So what about the second one? Do you want me to kind of go through all of these, or are you guys thinking you're good? Okay, let's go through. Okay, that's fine. That's cool. Hmm? This relates to whether f is a function because it is really checking whether f is a subset of the Cartesian product of x and y. Yep, yep. So this has to be true in order for f to be a function. Okay. And then the next one is saying for every element in y, w, um, every two tuple in f would have the second item, which is v, being different from this particular w. This has to do with surjection. Very good. Yep, exactly. Yeah, the first one will take you a little bit longer, but once you decode all of these quantified expressions, the other four questions is like bam, 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 right? Okay. So in this case, let's take a look at the function that we have, or at least we are taking a look at the set f that we have here. So d is map 2, okay? K is mapped 2, and then h is also mapped 2. So that means for this particular quantified expression, is it true or not? Is it true or not that at least one element of y is not mapped to? It will be false. Okay, they're all mapped to. Even though f is not a function, I can still evaluate this quantified expression. Okay. All right. So the next one, this one, the next two, just because this is by random, okay? So in this particular case, they just so happen to be right next to each other. They look similar, okay? Except one has two variables coming from y, the other one has two variables coming from x. That's the pretty much the only difference. Or the other side looks a little bit different too, but not by too much. Okay, so we'll handle the first one first. Okay. All right, so this one is basically saying I can find one element of y, one element from y, and one element from x, such that w does not equal to v. Okay, so we are looking at two different elements from y, which is quote unquote the codomain, and wu is in F. Okay, so I can find something in X, the quantical domain, mapping to U, and I can also find something that maps to V. Okay, that means one thing in the domain, quantical domain, is mapping to two different things in the codomain, and it is true in this case because C maps to H, C also maps to K. So it's true in this case. It relates to whether f is a function or not, and this needs to be false in order for f to be a function. Okay, are we okay with that? All right. What about the next one? Okay, because it looks so similar, maybe it has to do with whether f is a function or not. That is not the case. Okay, it has to do with injection. Okay, if this is true, then that means there are two things from the domain. Uh, Yes, it has two things from the domain mapping to the same thing in the codomain. Okay, so that means if number 4 is true, the function is not injective. Okay. Hmm? If it is true, then f is not a function. In this case, let me see. It's not because C maps to two different things. It is because both J and C map to K. Yep. So that's pretty much the five quantified expression, and then the answer to part five depends on that interpretation, and you have to tell me whether something is true or false, and that explains why it is a function or not a function, or if it is a function, whether it's injective or not. When I'm done, at least scanning all the exam, I can send you guys all the actual key to the exam. So basically, when I'm done grading, you will have a digital copy of your exam. You will have a copy of the key to your specific version of the exam, and also another file that will give you a detailed breakdown of your score. So that's going to be, what will happen? Okay, you will get all those three files in a folder that I share with you. So you don't have to do a single thing. That folder will just start to exist and you'll be able to view the content and those files will be in that folder. Hmm? It's going to be in my folder, but that folder will be shared with you. So you will have view only access to that folder. Yep. It took me a little bit of time to get all those scripts working, along with the grading spreadsheet and whatnot, but got everything working. Cool. All right. So are we all doing okay so far? Okay. All right. So we're going to go back to the lecture content now, okay, which is a little bit on the dry side. All right. So we are on propositional logic. So today we're going to dive into the actual symbolic nature of propositional logic. All right, so we're going to start with general propositional logic, which is quote unquote classical propositional logic. Okay, this is how everybody teaches discrete math. Okay, and then we'll get into a little bit of a deviation that is custom to this class. So there are four sets that are necessary in order to define a propositional logic system or calculus. Okay, these four sets consist of alpha, omega, zeta, and iota. Okay, so those are all Greek letters, but if you want to say A, omega, Z, and I, that's okay too. Okay, we don't have to refer to the Greek letters. So this is A or alpha. It is a set of symbols to be used, and symbols have no intrinsic or inherent meanings. So a typical, alpha set is going to look like this. So this is just typical. It doesn't have to be the case. Usually you have P, Q, R, S, T, or some letters coming from the English alphabet. So these are known as variables. They're Boolean variables. Each one can be true or false. Okay, so P, Q, R, S, T, the English alphabet letters are variables. They can either be true or false. Now, whether they are true or not, we don't know. Okay, we just know that okay, in this particular system, we have five variables, five Boolean variables. In real life, okay, when you apply propositional logic, PQRST, each one is going to correspond to some kind of statement that can either be true or not. Okay, for instance, okay, P can correspond to the statement that text class is absolutely boring. Okay, now whether it's true or not, I do not know. I just know that it is either true or false. Okay, Q, on the other hand, can correspond to Iraj's class is always entertaining. Okay, so it's either true or not. Okay, so that means each one is basically it's just a shorthand for a statement that can either be true or false. But there's one restriction: they cannot be quantified. Okay, so PKRST cannot say every ARC professor is boring. Okay, because we cannot express quantification with propositional logic. That is the job of predicate logic. So there's a slightly different logic system for something that has to be quantified. So the application of propositional logic is a little bit more limited because it cannot handle quantification, but it's a good introduction into mechanical logic derivation. And then we typically have some constants, okay? I personally just use 0 to represent false and 1 to represent true, okay? But if you want to say spell out true and spell out false, that's cool too, okay? I just prefer to use 0 and 1 for that purpose. And then you have some Greek letters, okay? So the Greek letters is kind of up to you, but I personally like to use rho, theta, and phi, okay? So this is phi. So, which three or four, whatever number you choose to use, is not really important, okay? So the Greek letters are known as schemata, okay? Schemata. It's basically the same thing as scheme, and then you say ata, schemata, okay? So schemata is basically, you can think of it as a variable that can hold an entire expression. Okay, so we have to defer what an expression is until we have talked about operators. So for now, we just say that well, the Greek letters are representing schemata variables or schemata placeholders. Okay, all right, so that's alpha. And this is representing a fairly standard set for alpha. Okay. So the next one is omega. Okay. Omega is a set of what they call connectives. Okay. So if you follow the actual term of classic propositional logic, omega is a set of connectives, which is actually spelled out here. But because this is a computer science class, and I assume everybody has taken CISP 360. So in our understanding, a connective is nothing more than just a Boolean operator. So connective is just a fancy word of a Boolean operator, which would be negation, conjunction, disjunction, implication, and equivalence. Okay, so those are the ones that we have talked about in this class. So in this case, I can say this is negation, conjunction, disjunction, implication, and if you want, we can also throw in equivalent to, or if and only if. Okay, that's just two names for the same operator. So these are the operators. So now we talk about, so with only alpha and omega defined, the next thing we need to talk about is actually not zeta and also not iota yet. We have to talk about the concept of a well-formed formula. So the concept of a well-formed formula is actually formally defined over here. So what that means is I have a predicate called is a well-formed formula. Okay, WFF is not a misspelling. It means well-formed formula. Okay, it is not a misspelled version of WTF. It really is just WFF. Okay, so this is an assertion. Okay, the assertion is if you take any element out of alpha, it is by itself well formed. So that means if I look at P as an expression, it is well formed, syntactically correct. Okay, if I take a constant, okay, like a 0 out of alpha, by itself, it is also well formed. Are we okay with that concept? Every element in alpha, when we look at it as an expression, it is by default or by definition well formed. Is that okay or not? It's just like in regular C++ programming, okay? Any integer constant is a well-formed expression of an integer. Does that make sense? Okay. All right. So that's the base case, right? It's the basis of syntax. Yep. No, it simply means every variable, every constant, and every schemata by itself is well formed. That's all it says. So 0 is well formed, R is well formed, rho is well formed, P is well formed, and so on. It's basically a syntactical qualification of whether an expression is well formed. So P by itself as an expression is by definition well formed. Yes. No, it means it is syntactically correct. It simply means it is syntactically correct. There's no compile time error. So from your perspective, syntax well-formed means it does not generate compile time error. There's no syntax error. Okay? So I'm just going to say 1, 2 as an integer is a well-formed integer expression. Okay? Does that make sense? Okay? So you have to start to introduce operators in order to say what is not well-formed. So because we're only talking about everything in alpha, so this E cannot involve operators because I have not introduced operators yet on the first line of what is well formed. Is that okay? All right. All right. So are we ready to move on to the second line, which is the recursive definition of what is well formed? We ready? Okay. So let's move on. So with this one, the first thing we have to understand is C is an element of omega n. You go like, attack. You never talk about what is omega n. Omega n is a subset of omega that consists only of operators that require n operands. Let me say that one more time. Okay? Omega n is a subset of omega of operators that involve n operands. Okay, let me ask you this question. How many operands does this operator require? 2. That is correct. Okay, very good. What about this operator in C++? 1. Very good. Okay. So for the most part, we are really only concerned about omega 1 and omega 2. Although you can go to any pharmacy and actually buy omega 3 and omega 6. I have to I have to try to keep you guys awake, okay? Because this stuff is dry. Okay? So are we good so far? Yes. The ternary operator is technically omega 3. However, it is not a Boolean operator, so it's not in consideration when we talk about propositional logic. You can also define like a AND operator that takes 3 operands, or you can define an AND operator that takes 4 operands, but those are not necessary because you can nest expressions. So that's why we only have omega 1 and omega 2. Yep. Yeah, the only way to express it is either prefix or postfix. Yep. Um, but we are, but typically we really, in theory, I mean, in practice, we only have omega 1, which is this guy. This is in omega 1. And then we have the rest being in omega 2. Okay. But the reason why I have to introduce the term of omega 1 versus omega 2 is so that I can refer to n as the number of operands. Okay, so that way I can now say for every I in the set of 1 to n, if phi of I is well formed and we have an operator C in omega n, which means operator C requires n operands, then we can imply that when you apply the operator C, which requires n operands, to the operands of phi 1 all the way up to phi n, then the resulting expression is also well formed. Is that okay? Is everybody okay with the recursive definition of what is well formed? Yes. Sure. Yeah, absolutely. Because and is it requires left hand side and right hand side. It needs two operands, and that's why it is in omega 2. Same thing with or, same thing with implication, and same thing with if and only if. Okay, so omega n is really just a name of a set that contains all the operators that has a left hand side and a right hand side. Whereas omega 1 are the operators, we only have one, okay, which is negation. It only has a right hand side, but not a left hand side. Okay, so now the question is, how do we figure out whether something is well formed or not? So at the bottom layer, we can say, oh, P is well formed, Q is well formed, R is well formed, blah, blah, blah. Everything from alpha by itself is well formed. Okay. Then you say, what if we apply an operator, but having the correct number of operands? So now we look at the AND operator. The AND operator says, okay, syntactically, I need a value. I need a well-formed formula. On the left-hand side, I need a well-formed formula. On my right-hand side, right? So that means at this point, you go like, oh, so if I put an R over here and take a P over here, this thing is well-formed. It is well-formed because we have two well-formed formulae to supply the values for something that is coming from omega 2. Is that okay? So this is well formed by itself. Okay. So, but something being well formed does not mean it has to be quote unquote meaningful. Okay. Because you can now say, oh, so tech, uh, false is well formed because it is in alpha, right? So that means false and false is also well formed. Yes, it is. It is syntactically correct. The compiler will not complain that you have a syntax error. Is it particularly useful? No, but it is syntactically correct. So now you can take this false and false, which is syntactically correct, and you say, can I nest this to itself to make a new expression that is also well formed? The answer is absolutely. Okay, so you say false and false is well formed, false and false is also well formed. If I have two well formed formulae, then I can use these two in conjunction with something from omega 2. And then the result should also be well formed. So that means this is well formed too. Is it useful? No, but it is syntactically correct. Okay. In other words, well formed is simply saying, okay, is the compiler going to complain about this? If the compiler won't complain about it, it is well formed. It is basically just defining the structure of the expressions that we're going to have to deal with. Are we okay so far with what the concept is about? Okay, what is well formed? So in your notes, okay, assuming you're taking notes, if you don't want to remember the term well formed, okay, you can just write down well formed equal syntactically correct or no compile time error. Hmm? Because this way you're not going to force a type coercion in JavaScript. You can actually see the number of stuff that I'm trying to teach in the same class, which most of it you will not totally remember until you actually run into it. You go like, oh yeah, I remember Tech said something about that, but then I have completely forgotten what he said. That happens to me too, so it's okay. All right. Okay. So are we okay with these two lines here, which is the recursive definition simply saying, okay, is this expression syntactically correct? We good? Okay. So once that is good, we can actually now go back to not to talk about zeta, but we skip zeta to talk about iota. Okay. So iota is a set of well-formed formulae, and that's why I have to talk about well-formed formulae first. It's a set of well-formed formulae that are known to be true. Okay. In other words, these are axiomatic. Okay. Do not ask me why it is true. So now you ask, so what can potentially be in iota? It really depends on quote unquote reality, the reality that your propositional logic system is trying to model. Okay. In other words, okay, if P means tech is absolutely boring and Q means Iraj is absolutely boring, then you can say, "Hmm, from what I was told by other people, um, P or Q is true." In other words, you only know that at least one of Tech or Iraj is absolutely boring. Now, is it Tech who is absolutely boring? Is it Iraj who is absolutely boring? Or is it both of them? Well, we don't actually know. We just know the expression is known to be true. Is that okay? So iota can contain stuff like this. Okay. In other words, what elements you put into iota depends on quote unquote the reality that you're trying to model. We good so far? Yes. Every element is a well-formed formula, and that for that element, it's assumed to be true. So that means we can quite easily throw in a 1, okay, because 1 is a constant. When 1 is in alpha, it has no meaning, okay? It is really literally just a symbol. It is a token. Using the AI terms, it is just a token. But once we put 1 into iota, now it has meaning. It means that that constant means true, okay? Yes, that would not be good because now your system is going to have some problem with the derivations. So you don't want it. You don't want contradictory stuff to be in your iota. Okay. So you can also put in other stuff. Like t. Huh? Yes, you can put in not zero. So not zero is fine in iota. But you can also have your p implies s. Okay, which is basically saying your p is tech is absolutely boring and S can mean you can enjoy a nice little nap in text class. Okay, so P implies Q is known to be true. Okay, in other words, it doesn't say a single thing about whether I'm actually absolutely boring or not. It is only saying that if tech is absolutely boring, then you can get a good rest in text class. Is that concept okay? It's the implication itself that is known to be true, but it doesn't say anything about whether the left hand side or the right hand side is true or false. It is the statement that is known to be true. Yes, once it's true by itself, it is a constant. If you want to do it that way, you can also have some additional statements here. So if you want to say, okay, when is Iraj's class? Right after this one? Okay. So you can say something like P or Q implies, we'll pick another one, implies T. Okay. But in this case, T is something along the line of you're going to have at least 1 hour and a half of good rest in the afternoon on a Wednesday. Does that make sense? In other words, the last statement here, this implication, is saying one, P is tech is absolutely boring. Q is Iraj is absolutely boring. It is saying if tech or Iraj is absolutely boring, then you can have at least 1 hour and a half of good rest on a Wednesday afternoon. Yes. not necessarily connected. Okay, okay. So are we doing okay so far? Well, this is a implication, right? So when you look at the left-hand side versus the right-hand side of an implication, the left-hand side implies the right-hand side, but the other way to say that is if left-hand side, then right-hand side. Yep. Question? Mm-hmm. Mm-hmm. Yes. So iota can only be a set consisting of well-formed formulae. Has to be well formed. Yes. So every element of iota has to be well formed. So in this case, they are well formed. P or Q is well formed because or is from omega 2, P is from alpha, Q is from alpha. We're good. 1 is from alpha, it is by default good. P implies S is also good because P is from alpha, Q is from alpha, implications from omega 2, we're good, and so on. Okay, so iota is your basis. Okay, this is your quote unquote reality basis. Okay, what do you know about this reality? Is that okay? All right. Mm-hmm. Okay, so I can introduce one more. Okay, so you can also say the negation of t is true. Okay, in other words, everybody in this semester complains about, you know, in the afternoon of Wednesdays, I could never really get a good rest for at least an hour and a half. That is also true. Okay. So now the question is, can you prove stuff? Okay. So the whole system, okay, which is what Zeta is about transformation, which is about proving stuff. But at this point, are we okay with the meaning of the iota set? Okay, it is quote unquote, okay, a summary of the reality that you want to model. Things that are known to be true to begin with, axiomatically true. Are we good? All right. So now we move into zeta. Okay, so zeta is a little bit funky because each element of zeta is what we call a production or an yeah, we'll just call it a production or transformation. Okay, so now we take a look at zeta. So we'll talk about a few elements of zeta. Okay, so we'll say a particular element is in zeta. In other words, I'm not enumerating everything that is in zeta. I'm just telling you what potentially can be in zeta. So we'll start with something that is relatively simple. Okay, we will say um, the left hand side of this symbol, which is infers. Okay, so this is also known as infers. Okay, not implies. Okay, there's a big difference between implication and inference. Implication depends on meaning. Okay, it depends on the truth table. It depends on meaning. Infers simply means if the requirement is satisfied, we can fire this rule and then create whatever the right hand side is creating. It is completely a syntactical operation. It doesn't really care about logic. It is just a syntactical rule to say that if certain things are satisfied, specified by the left-hand side of the inverse symbol, then whatever is specified on the right-hand side can can be labeled as true as well. Okay, so now we'll take a look at something like this. Okay, which one? This one? No, no, I just erased it because originally I was trying to enumerate all the members, but I decided against that idea. So I'm giving you specific members of Zeta. So we'll say, okay, this is where the Greek letters come in, okay, which is basically a placeholder. This is theta, and in this case, this particular set only has a single member of theta. The inverse on the other side is saying theta or not theta. Okay, so we'll take a look at this whole thing. This is one single element of zeta. Are we good so far? Okay, so I'm only specifying an element of zeta in classic propositional logic. Yes. Hmm? Set A. Oh, because I erased it. It wrapped around on the next line and I erased the following line. Yep. The continuation would be the Greek letters, like theta, rho. I think, what was the other one that I was using? I like to use psi too. Sometimes I use phi. It doesn't matter which Greek letter you want to use. As long as it's Greek, it's all good. Are we good so far? Okay. So now we have to take a look at this particular production or transformation rule and say, what does that mean? Okay. What that means in this case is easy. Okay. This particular set is giving you constraints. Okay. In this case, the constraint is just like, okay, give me a well-formed formula that is true. Okay. We go like, oh yeah, we got a bunch that we can use. Is that okay? And it once you satisfy the requirement of the left-hand side, then we say this resulting expression is going to be true for sure. Is that okay? So let's see what we can actually do in this case. Okay. So now we can take a look at all the elements in iota, right? So we have P or Q. Okay, let's pick P or Q. The question is P or Q as an expression true? Yep. Well, it is in iota. By definition, everything in iota is axiomatically true. So we go like, okay, fine. Okay, theta can be instantiated as the expression of P or Q. Okay. Hmm? Yep. You can pick anything. You can pick any expression that is true for theta. Because we only have theta by itself, that means we basically don't have any restrictions. Okay. And then later on, we'll pick something that is even more awkward, but it's okay. We'll in fact, okay, let me change this a little bit because I want to present. This is true. Okay. This is fine. But this is actually a little bit better. It makes a little bit more sense because if theta is true, then theta and theta is going to be true too. Okay? But remember, this is a syntactical operation. It simply means go find me something that is true. Okay? Quote unquote. But being true is nothing more than a label. Okay? It's not the same as the expression being evaluated to be true. It is simply labeled to be true. So we pick up this guy from iota and we say, okay, this is true, okay, because I was told it is true. Okay, cool. So now we can say P or Q and P or Q is also labeled to be true. Does that make sense? Yeah, I think it makes sense. Okay. So there are other rules too. Okay, so I can give you another rule. I'm gonna erase this side of the whiteboard. So now I can give you another rule in Z. This one is awkward. Okay, is an empty set. In other words, I'm not looking for any pattern. Then what can you possibly infer? Well, we just say theta or not theta is true. So that means theta in this case has no can it only has to be a well-formed formula. Okay? But it doesn't have to be labeled true to begin with. Does that make sense? Okay, let's pick something that is not in iota. Okay, let's pick mm, Q by itself. Okay, do we see Q anywhere? In Q is not there, right? But yet I can say, we can instantiate theta to be Q because Q is not in the set that is on the left-hand side of the infer symbol, which means I have no restriction now. Okay, any well-formed formula can be my theta. There's no requirement. Okay, so then this thing fires. Okay, when it fires, then we go like, okay, Q or not Q. Oops. Okay, Q or not Q as an expression can be labeled true. But it kind of makes sense, even though it doesn't seem to be very useful. It does make sense. Yep. No, we do not. Well, in fact, we know Q by itself is not axiomatically true. Now, can we prove whether Q is true or not? That's a whole different thing. Uh-huh. Yep. Okay. So these are two examples. So this is also, traditionally one of the transformations that we usually put into zeta in classic propositional logic. Then you guys go like, well, looks like we really do not need multiple Greek letters in this case because we only use one at a time. Well, that is not entirely the case. So now we can say something like, eh, okay, we can do this. So now we can say, now we have two elements in the set, okay? So this set now says phi implies psi, and it also has another element. The second element is phi by itself, okay? So now this is a little bit more restrictive, okay? Because what it is trying to say is, okay, give me an expression, a well-formed formula phi that is true. That by itself is not a big problem. But the other expression that I also needs to be true is the same phi implying some psi. Is that okay? So I'm now putting a structural requirement to the two expressions that need to be true. Because these are not just any two random well-formed formula that is true. It has to be one has to be the right-hand side of the other one. The other one has to be an implication. So now I'm giving it structural requirements. Are we doing okay so far with this? We good? Okay. So this particular rule in classic propositional logic is saying that infers psi. That is the rule. It is a transformation rule. It is an element of zeta. So what that means is if you can somehow show me an implication, okay, that is true, and then somehow you can find out that the left-hand side of that implication is also labeled true, then I can infer and basically I can now label whatever is on the right-hand side of the implication, in this case psi, is true. Now, does it actually reflect the way we define the operators? The answer is yes, okay? Because it's important that the transformation rules are sound, which means they have to reflect actual logic systems, okay? Which basically also means you can have a transformation system that does not actually match the way we define the Boolean operators, then whatever it derives is pretty much useless. Are we okay so far with this one? Okay. So can we fire this rule given just what we have in iota? I think so. I think we can do this, right? So in this case, I think our phi can instantiate to P or Q, and then our psi can instantiate to T. Does that make sense? Okay. So now, if this is how, so let's check the requirement, okay? First of all, is phi by itself a true statement? This particular phi, the way it's defined. Yes, because it's in iota, right? Um, can we find an implication where the phi is on the left-hand side and the implication itself is also true? Yeah, we can find it. It's right here. Okay, so whatever t is now psi. Is that okay? So I'm only giving names to the structural parts of things that match. Is that okay? So once I satisfy the matching requirement on the left-hand side of the inference, I can now say, oh, okay, cool. Whatever is on the right-hand side can also be labeled true. And in this case, this means, t as an expression is also labeled true, which basically means, I should not have not t in iota to begin with. Is that okay? Any questions about this? So the classical propositional logic system has 20 something rules like this. Okay, they're it's complete, which means if something can be proven, you can use that system to prove that it is true. Okay, so now what I want to do is to take a look at this from a quote unquote space perspective. Okay, now this space is not a two-dimensional or any particular dimensional space. So it is a space. I'm going to use this green line here to define the boundary of the space, but that space is actually infinitely large. In other words, the green line is defining the space of all well-formed formulae, okay? Including things that we don't know whether it's true or not, okay? It's just syntactically speaking. Everything that is syntactically correct is within this green box here. Is infinitely large, but I cannot draw an infinitely large square, so we just pretend this is infinitely large. Is that okay? All right. So if that is the case, what is iota? Well, iota corresponds to dots within that space. Okay. So we'll use the red pen here to identify things that are true. Okay. So initially we have one dot corresponding to P or Q. We have another dot here corresponding to 1. We have another dot here corresponding to P implies S. We have another dot here that connects to P or Q implies T, and so on. Okay, so all of these are little dots within the green square. Are we doing okay so far? So what is the difference between a dot that is red versus the implicit dots that are just everywhere? Well, the ones that are red are known to be true, either because they are in iota or they are known to be true because we fire some of the rules in Zeta and we can label it to be true. So now, when we look at this particular rule, okay, the last rule example, okay, which is this one here, we go like, okay, so what is happening here? So what's happening here is we originally have an expression. We'll just use a blue dot here, which is t. Okay, we go like, no, t is not in iota. It's not by default labeled red because we really don't know whether it's true or not if we just observe iota. Is that okay? Okay. So now we look at this whole thing and we try to correspond to the firing of this particular rule over here. We go like, oh, okay. Since we can fire the rule of um, phi implies psi and phi in a set infers psi. Since we can fire that rule, that means I look at this dot, which is t as an expression, and go like, oh, I got good news for you. I can now change its color to a red. That is how, this is one way to visualize, how we apply the rules in Zen. Okay, we are basically looking at all the dots that are already red, and then we just say, can we use these to fire this particular rule? We can. Okay, let's label that one as red as well. Yes. No, you're not adding t to iota because t is derived. So axiomatic. Axiomatic means it is by, you cannot question or know why they are true. They're just true by definition. But t is not true by definition. T is derived to be true. So if you're more kind of a visual person, now you can say, oh, let me see if I can do this in a visual way. We start with this dot here. We start with this dot over here. Okay. And if you like to, kind of name the rules, okay, we'll just label this one as number one. Okay. It's just a name. Okay. That's all. So you go like, okay. They meet the left-hand side of rule one. That means I can now label this little expression here red because we now know that t as an expression is true. Is that okay? That is the basic mechanism of propositional logic. Okay. So what is the application? What do we want to do with propositional logic? So the idea of propositional logic is you want to know whether a particular expression is true or not, whether it can be implied by iota or not. So we'll just, just for the sake of this, particular argument, this little blue dot here is S or T. Okay, is S or T in iota? Do we know for sure it is true? No, it is not axiomatically true. So now the question is, if I keep applying these rules, can I change this dot corresponding to S or T from blue to red? That is the question. Hmm? Hmm? Yes. Well, okay, but the question is, you cannot apply just normal intuitive reasoning. You have to use only the productions in Zeta, okay? Because the whole idea is we want to do this mechanically. Yep, go ahead. It is solved. Basically, if you look up propositional logic in Wikipedia, they give you like 20 something rules that we already know would represent, the Boolean logic system that we use. Yeah, so the whole thing is already known. The rules are consistent with actual Boolean algebra. So the rules are not true or not. They just have to be consistent with Boolean algebra. The truth tables basically that we have. Yeah, yeah. So now, okay, because this would be a good way to end the class, is so what are we really trying to do? Well, we are trying to, there's a little blue dot, okay, somewhere that has a complicated expression that we want to know whether it's a consequence of iota or not. Okay, that's what we want to know. The productions is basically saying, okay, I can tell you how to connect the dots. Okay, I can tell you how to connect the dots that are red to begin with, and then spread that red all over the place. The question is, can we eventually spread the red labeling to the dot that we are interested in? That is the question. That's basically how we prove theorems in any branch of mathematics. You start with things that are known to be true. Some of those are rules like, commutative rule, distributive rule, and so on and so forth. And then you're also given certain constants, okay? A equals to b squared plus c squared. And you're trying to derive a certain expression that is also true, okay? So basically, this is what we want to do. But there's a problem with this. Okay. The problem with this, if you want to do it in an automated way, because my focus is not whether we can do it. Okay. My focus is, can you program a computer to do this? Okay. So the problem with this is twofolded, or actually, there's only one big problem. It's an infinitely large space. So now you can imagine that you have a haystack that is infinitely large. Okay. The one little thing that I'm trying to see if it can be labeled red or not is a needle. So now we're trying to find a needle in a haystack. Usually, finding a needle in a haystack means it is tedious. I don't want to do it. Okay. But in this case, it may be not possible because you have an infinitely large haystack and you're asked to find a needle within that haystack. Can you differentiate the two cases where one is the needle does not exist in the haystack versus you have not found it yet? The answer is no, you cannot really differentiate between those two cases, and therefore we have a problem. Do you all understand why we have a problem? When the haystack itself is infinitely large, and you're supposed to find a needle, and you don't even know whether the needle is there to begin with. So the problem is we can't solve that problem. Okay, so traditional or classical propositional logic is great if you already know this dot should be red to begin with. Then it's just a matter of time before you find it. But if that dot is not even known whether it should be red or not, then we have a problem. Okay, so my modification to the propositional logic system is one, confining that space to be finite. Okay. Two, each time you apply a transformation rule, the resulting expression is simpler than what you start off with. So that means repeated application of those rules will basically just get things becoming simpler and simpler and simpler. So that means, you will get to an end. The algorithm will terminate. It will either tell you that the dot that you're interested in should be red, or it cannot be red. Because your haystack is now finite. You can actually comb through the entire haystack and confirm that the needle is not in the haystack. So that's the whole reason of why we will talk about resolution. And because of resolution, we'll also talk about conjunctive normal form. So those two are really related. But those two will work together only with proof by contradiction in order to prove whether something is supposed to be read or not read to begin with. Okay, so that's kind of the roadmap of what we'll be talking about. So today's lecture is just introducing the classical propositional logic system, which is typically what most people would end this entire discussion with. Okay, if you take this class with any other college, that's pretty much where they will stop, and they will give you some exercises, do it by hand, da 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 da. I'm not going to do that, okay, because that is useless from the perspective of computer science. I want to take this one step further so that we can actually come up with a mechanism that can automate theorem proving, given that we're only dealing with propositional logic. So that's what we'll be doing, I guess, for another week or so. Um, but it really helps if you read ahead of time because this stuff can be a little bit abstract. So just getting some idea of what terms we'll be talking about and how those terms are interconnected is going to be helpful because now you have the context in your mind before you come to class. So I highly recommend reading a little bit ahead of time before Wednesday. All right. So see you all on Wednesday. And according to this, you will get a restful, you will get some rest, on Wednesday in the afternoon. But I'm not saying who's the boring one. Yes. Hmm. Yes. we're trying to use the green lines, the connections, to see whether the green lines would eventually connect to this dot so that we can turn it from blue to red. Hmm.